I'm your host, Kitty. Today, our webinar topic is Getting to Know HDFS. It is a continuation of the Hadoop webinar series. We have Gene Tang here with us today. He is the solution architect in Rackspace Asia and also the big data subject expert in the region. If you have any questions about this webinar, please type them in the chat box. We will answer that after the session. Now I will pass that to Gene.
Thanks, Katie. Welcome everyone to this webinar. As Katie mentioned, the topic we're going to be talking about today is HDFS, the storage element behind the Hadoop ecosystem. So we're going to be covering off a number of topics today, starting with simple HDFS concepts, then talking through the architecture and administration of an HDFS environment matched with some demos. Now, that's a lot to cover off in a half-an-hour session, so it does mean we are only going to scratch the surface of HDFS. Naturally, HDFS has a significant amount more depth to it, but I do hope that this presentation does inspire you to delve further into HDFS, and also ask questions at the end of the session, which I hope to be able to answer for you. So let's start by briefly recapping over what HDFS is. HDFS is the Hadoop Distributed File System. Now the keywords in that are distributed, meaning that it's a file system that exists across a number of different physical servers, and the word Hadoop, in which this file system was specifically developed for Hadoop and big data analytics, and it remains the default file system for most Hadoop distributions. Now the latter point is really important. HDFS is not designed to be a general purpose file system like NGFS or ext4 and currently used as such. It is a file system that is purpose-built for big data analytics. And this means that it's optimized for things like large data sets, where large is often measured in hundreds of gigabytes through to petabytes. It's also optimized for streaming data access as opposed to interactive access. Because datasets are so large, HDFS will stream the dataset bit by bit to an application which processes it as a stream. If we were to go the other way and have the dataset loaded and only process the dataset once it's completely arrived, this would not be viable because of the size of the datasets that we are considering here. This does mean, though, that HDFS is considered a high throughput file system as opposed to a low latency one. And it's for this very reason why HDFS appears to perform quite sluggishly when we try and access it interactively. Also, HDFS is designed as a write once, read many file system. Now, reading data is the primary characteristic of an analytics application. Very rarely does an analytics application need to modify data once it's in place. And therefore, HDFS has no facility to modify a file in place because it very rarely needs to be done. So if you do need to modify a file, what you need to do is you need to download it from HDFS, modify it on your local file system, and then re-upload it to HDFS. Now, from an architectural standpoint, HDFS is also a very highly scalable system. And this scalability is achieved through the fact that HDFS is distributed. HDFS clusters often can measure in the hundreds, if not thousands of nodes, and this level of scalability helps HDFS achieve its big data scale. Additionally, HDFS is designed to run on commodity servers, and this is an important element as to why Hadoop has become so prevalent, because through the use of lower-cost hardware, we naturally have lowered the barrier of entry to big data analytics. Additionally, it is considered a highly durable and fault-tolerant file system, owing to the fact that lower-cost servers do tend to have higher failure rates. Preventing data loss was a key driver for the developers of HDFS, and their approach to improving durability was through replication, where we would create multiple redundant copies of data in the cluster, so that if you lose one copy, you always have another copy to turn to. Now, the final characteristic of HDFS that I'll mention today is that it is a portable file system. This means that HDFS can be run on many different operating systems like Windows and Linux with very few changes. And it owes this characteristic to the fact that it is developed in Java. Why I mention this characteristic is because it helps better conceptualize what HDFS actually is. Now, looking at the diagram on the slide, HDFS is a file system that actually runs on top of another general purpose file system like NTFS or ext4. It is also distributed across a number of different machines as opposed to a general purpose file system that would be constrained to a single machine. Now, let's have a look at this in action. Here I've got two Linux machines. They are also running HDFS on them. So if I were to show the process, we have an HDFS process running on both of these machines. Now, as mentioned previously, HDFS does exist as an abstraction on top of your general purpose file system. This means that from one machine we will have access to two different file systems, one local file system and one distributed file system. And I'll show you them both here. Here we have the local file system, which is running ext4. And we also have another file system, the HDFS file system, which is located there. Now, HDFS and the local file system are independent to each other. If I do make a change to one file system, it should not propagate to another. So I can show that by creating a new file. You can see the new file here on the local file system. And if I have a look at HDFS in /temp directory where I create the original file, you'll also see that that file does not exist. In this way, HDFS, although it sits on top of your local file system, it does run separately to it. Now, HDFS is also distributed, and this distributed nature can be seen if I can access the file system across two different machines. So let's go ahead and do this. So here I can access the file system on one machine. And I can also access the file system on the second machine. And you'll note that these file systems are identical. But I'll take this one step further. If I were to delete a directory on one machine, let's say test1/test1. If this was a distributed file system, I should see that that test1 directory no longer exists. We'll run this on the second machine, and you'll note that the test1 directory no longer exists in that root directory. So the changes to the distributed file system, as you can see, will propagate across that cluster. So back to the presentation, I want to talk a little bit more around the mechanics of HDFS. Specifically, I want to talk about how data is stored in HDFS. Now, looking at the diagram, when data is uploaded to HDFS, it is first split up into even chunks known as blocks. Now, these blocks are used configurable in their size, and in the diagram, the data set itself is split up into 6 different blocks. Now, these blocks are then distributed and stored in servers across the cluster. Some servers may receive no blocks, whereas other servers may receive more blocks than others. Subsequent to this, these blocks will then go through a process of replication, in which case HDFS will automatically create copies of those blocks onto other servers with the purpose of improving data durability. Now, in this way, if I lose a whole server, I have another server to go to access that data. Now, data blocks themselves are stored on servers, which in the HDFS context are known as data nodes, where each server will run a data node specific service. But in addition to the data node service, there still is a need for a control service, one that records and tracks block placement, one that responds to client requests for data access, and one that monitors and maintains the healthiness of the cluster, for example, controlling that replication. And this metadata service is known as the name node service. Now, the name node service should, best practice, exist on a separate machine, and in itself is at the center of HDFS and performs all control and monitoring functions. So this means if a client wants to store data on HDFS, for example, the client must talk to the name node first, who will then inform it of an appropriate data node for which to store that block of data. The client will then contact the data node, who will stream the data into the node, and that will naturally set up a replication process, which again is controlled by the name node. Similarly, if a client wants to read data from HDFS, the client needs to contact the name node, who in return gives a list of blocks and their locations for the specific file. After this, the client will directly contact the data nodes to get the individual blocks and then reassemble that file. Now it's clear here that the name node is pretty critical to HDFS. If you lose the name node, you lose all ability to access your data. And this really emphasizes the importance of high availability and redundancy of that name node. It's perhaps quite surprising then that in Hadoop version 1, by default, there was no functionality to make the name node highly available. There did exist a configuration known as the secondary name node. However, this was not a mechanism for high availability. Instead, the secondary name node simply performed a function known as checkpointing. And really, the secondary name node name was a poor choice of naming. But come version 2 of Hadoop, though, an option for name node high availability did become available. And this configuration was known as the standby name node. Now, as you'd expect, the standby name node will automatically resume the role of the name node if the primary name node were to fail. And this configuration requires at least 3 master servers in order to work correctly. Now, I'm not going to go into too much depth around the name node and name node high availability configuration. At this stage, I simply want to make you aware of it. Now, this leads us nicely onto talking about architecting a HDFS environment. Architecting an HDFS environment is just as much an art as it is a science, because the most optimal environment always depends on your environment, the data you have, the application you've written, and the usage of that environment. But as with any environment, there naturally needs to be a starting point. And this starts with sizing the hardware. Now, as mentioned previously for name nodes and data nodes, we should be using commodity servers, preferably rack mount servers like those from Dell or HP. Sizing the name nodes in particular is very simple. Given that the name node is pretty critical, you do want a reliable server for all your name nodes. It should have mid-range performance, and this means, for example, server-grade processors like Intel Xeon processors, as well as around 64 gig to 128 gig of RAM. So the general rule of thumb for RAM sizing is about 1 gig of RAM per million blocks of data. And you should also use SAS and RAID. SAS provides better performance and reliability than SATA disks without the high cost of SSDs. RAID provides that additional data redundancy to ensure reliability. The key thing here, though, is that we shouldn't skimp on reliability and performance, as these servers are critical to our environment. Now, sizing the data node hardware is a little bit more complex, since this is where the data is stored and where the work is done. Now, reliability isn't key here with HDFS, with the data node, as HDFS can cope with a lot of the data nodes pretty easily. But we do want to choose a commodity server that has a high disk density in order to minimize our costs. In terms of CPU and RAM configuration, this is dependent on your workload and is something that we will explore further in future episodes. But it's the sizing of the disks of the data nodes that is more relevant to this conversation and does follow a basic process that I will describe here. And this process starts with answering two questions. The first question, how much data do I need to keep? And the second question, how many servers do I have for data nodes? This naturally will open up other questions. For example, for the first question, how much data do I need to keep? We need to consider things like data retention periods as well as data growth rates. Now, the first step to sizing your data node disk configuration is to calculate the total amount of raw storage that we need. Now, this isn't the same number as the amount of data that we need to have or need to keep, as this number doesn't factor in the replication factor as well as the swap space. To get the total amount of raw storage, we need to start with the amount of data that we need. In this example, I'm using 15 terabytes. We firstly need to multiply this by the replication factor. With the default being 3, we're going to multiply the 15 terabytes by 3 to give about 45 terabytes of storage. Secondly, we need to factor in a swap space. The swap space is a working space for our application to function correctly. And a good rule of thumb is about 33% of the previous number. So multiplying 45 terabytes by 1.33 or 33%, that comes out to about 60 terabytes of data so far. Now, sometimes we may compress our data. Now, compression is an advanced topic and something we will explore in the next episode, but it is a common mechanism to save space. Now, the compression ratio is dependent on the codec or the compression algorithm. With something like bzip2 and its compression ratio of about 2 to 1, we're going to use this compression ratio of 2 to 1, and that means that we can lower our storage requirement to about 30 terabytes. Now, using this number, we need to determine how much storage each data node must have in order to get the correct disk configuration for each of those data nodes. Now, in this example, I've got 4 data nodes that are available. Now, the first step is to ensure that this number is greater than or equal to the replication factor in order for replication to work, and in this case, it is. Next, I need to divide 30 terabytes by 4 servers to find out the per node storage requirement, coming out to about 7.5 terabytes per data node. Now, because the data nodes don't need to be hugely reliable, we can use a basic disk configuration with no redundancy, like a JBOD disk configuration. Now, assuming I have a 2 terabyte nearline flash disk available, it means I only need 4 disks per data node. Now, this is the final number of disks we need in each data node to meet our data requirements. Now, combining this with either a 1 gig or a 10 gig networking on a flat network segment, and then we'll likely have an environment that will work well for us in our HDFS cluster. Now, at this stage, I want to talk a bit about the operational aspects of HDFS. Using HDFS and navigating around HDFS is relatively straightforward and should be very familiar to Linux users. The command at the top of the slide, HDFS DFS, followed by a file system command and a file path, is the generalized command you would run in the Linux shell to perform basic administration of HDFS. The table lists some of the common commands, and as you can see here, the commands are very similar to what you would use in a Linux shell. For example, ls would perform a directory listing, and rm would perform a delete. Slightly different to this though, and one that I want to highlight, is this final command in the table at the bottom. Copy from local uploads a file from the local disk to HDFS. Now remember, HDFS sits as an abstraction above your general purpose file system. So if you want to put files into HDFS, you need to perform an upload command with this particular command. Now the link down the bottom provides a more exhaustive list of commands, including how to download a file from HDFS into your local directory. So check that out if you want a more complete list. Now at this stage I'm going to switch over to my demo machine so I can show you some of these in action. So the first thing I want to do is to use the basic file directory listing and show you how to list the contents of a directory. And this is done by using HDFS dfs-ls, very similar to Linux. And in this case, I want to do a directory listing of the root directory. And there you go. Next, I want to show you how to make a directory within HDFS. Again, very similar to Linux. HDFS dfs mkdir maker. In this case, I want to create a directory temp2. And as you can see, the temp2 has been created. Again, delete. Very simple. HDFS dfs-rm. Because I want to delete the temp2 directory, I need to use the -r flag for recursive, and temp2 should now be gone. Now the permission structure in Linux, in HDFS, is actually very similar to that in Linux. As you can see here on the left-hand side, we have the user here, the user, the group, and the other permissions. Similarly, we have an owner and a group owner. Now, as you'd imagine, HDFS has very similar permission commands as Linux. chmod as well as chown do exist. In this case, I'm going to change the /test directory to have full permissions. So HDFS dfs-mod 777, again for everybody, /test0. And as you can see now, that directory has full permissions. Now the last thing I'm going to do is upload a file into HDFS from my local file system. So I'll create a file, test file abc, and I would use HDFS. There is multiple commands that you can use to upload a file. There is a -put. But in this case, I'm going to use copy from local, so that's copying from the local directory into HDFS. Specify the file, and specify the directory in HDFS you want it to go into. If I do a directory listing of /temp, you can see here that this file has now been uploaded. Now, as an administrator, you often need to make changes to an environment with Optimizer, and HDFS has numerous customization options. All these customizations can be modified via the HDFS-site or XML file, which is located in the default Hadoop configuration directory, which is shown at the top of the slide. I have listed a few example options on the slide, which we have talked about today. Firstly, dfs.replication defines the replication factor for HDFS. Now, by default, this is 3. It can be changed to any number you wish, provided you have sufficient space. Next, you have the DFS block size, which defines the block size of HDFS. By default, this is 64 megabytes and can be changed to any number you require. And I want to highlight this specific option because knowing the block size and being able to change the block size can have a major effect on how efficient your jobs run. And so it's an important option to recognize. Lastly, dfs.host defines a list of servers that can connect to HDFS. Now, a more comprehensive list of these options can be found at the link at the bottom of the slide. Now, HDFS also has a few advanced administration commands. Firstly, HDFS SSDK performs file system checks. HDFS dfsadmin is really a toolbox of HDFS utility that you can use to do things like enter safe mode, upgrade HDFS, as well as refresh the nodes in a cluster when you've added or removed a node from the cluster. And finally, you have HDFS Balancer. This utility allows you to rebalance your cluster when data blocks become unevenly spread across data nodes. Now again, switching over to our demo machine. Firstly, I want to show you the HDFS-sites.xml file running on the main node. Now this is located within the default configuration directory for Hadoop, which is located here. Now opening up that file, you can see that there is a lot of options in the XML formatted. Now specifically, I want to point out the replication option. You can see the default is 3, and this value can be changed very easily. And similarly, here we have the block size. This number is 256 meg, and it's in bytes. Now, exiting the config file, let's have a look at some of those administration tools. Firstly, FSCK allows you to determine the healthiness of the file system. So HDFS FSCK on the root directory will let us know whether or not that file system is healthy. Now, if it's unhealthy, it may suggest that you have over-replicated or under-replicated blocks. This could be due to the fact that a node has been introduced or a node has been removed. Similarly, you can also use FSCK to determine the block size of the files. Now, previously, I've entered or uploaded 2 files with different block sizes into HDFS. So I can use FSCK to have a look at that file. This Wikipedia-small.xml has a block size located here of about 64 megabytes. And I have another Wikipedia file which I've uploaded, in this case, with a 256 megabyte block size. Now, moving over to HDFS dfsadmin. Again, this is a toolbox of utilities, and these are some of the options that you can utilize with dfsadmin. You can run a detailed report detailing the state and the healthiness of your HDFS cluster, and this is broken down by data node, you can see here. And you can also use dfsadmin to enter safe mode. Now, I'm not going to enter safe mode at this stage, but safe mode is an option particularly useful for maintenances and upgrades where you want to place your name node into a read-only state. Now, I want to end this presentation by talking a bit about some HDFS alternatives, because it's important to be aware of other alternatives to ensure that HDFS is best for your situation. Now, there are a few alternatives to HDFS in the market. Ceph, the well-known open-source distributed object store and file system, can be used as a drop-in replacement for Hadoop. Similarly, IBM's GPFS, or General Parallel File System, is a hugely scalable, proprietary distributed file system that's actively being developed as a replacement for HDFS. Probably the most well-known alternative is NetHa's proprietary file system known as NetHRFS. It is considered faster than HDFS and has the added advantage that it can be mounted as an NFS share. Additionally, it does provide functionality such as snapshots and mirroring. Now, another really interesting and up-and-coming file system is Tachyon. Tachyon is an in-memory distributed file system designed to be compatible with Hadoop. Given its in-memory nature, it is designed for high speed and matches projects like Spark very, very well. Now, it's an open source project and has only been a project since about 2013, so it is relatively immature, but in saying that, it is being used in production by companies such as Yahoo and Baidu. So this brings this presentation to a close. HDFS is a key component to Hadoop and is starting to establish itself as the de facto standard for big data storage systems. I do hope that through this presentation, I've given you a really good insight into HDFS, and I would like to thank you for attending, and I hope to see you next time.
Thank you, Steve. So If you have any questions about the webinar, please type it in the chat box. So if there's too many questions and we need to stop it, we will answer that in our blog post later, and we'll send the link back to you guys for your review. So we got a question from Karthik. So can a name node also be a data node? So basically, can she set up a HDFS cluster on just her laptop?
Yes, you can. You can have a data node and a name node in the same server. And that's really ideal for kind of a test environment as it is for your case. In production, naturally, you do want to separate the name node and the data node, especially if you do want to do high availability for the name node, and there's a definite requirement to separate those out. The reason for separation is really separation of duties as well as performance. There are some distributions, and I want to mention this as a separate note, there are some distributions such as MapR, which allows you to have control of data nodes in production systems. So that's very specific to the MapR distribution.
Okay, so next question we got is is asking about, can you use HDFS as a file system for Linux?
So this goes back to one of the previous slides with regard to HDFS being specifically designed for big data analytics. The simple answer to the question is no, it cannot be used as a replacement for a Linux file system, as it is an abstraction on top of a Linux file system. So you can't, for example, install applications on it.
Okay, I think it's about time in order to verify the local time. So for any other questions, we'll jot that down and then we'll reply on a blog post and send back the link to you, all of you, for your review. So thank you for your time. We'll also have our webinar on April. We'll send an invite to you all and hope we can see you at that time again. Thank you. Bye.